Good day and welcome back for part two of our discussion on limits and continuity. In the previous video, we introduced this idea of evaluating a limit of a function of two variables. And to begin, we're really focusing in on showing when a limit does not exist. If you can find two different paths, in this case, approaching 0, 0, where the value of the limit is different, that would allow us to conclude that the limit does not exist. So in terms of approaching the origin, there are many different paths that we could choose. Now, one that's extremely easy for us to work with would be a vertical line or a horizontal line. So for example, we can say we approach the origin along this horizontal line, so we might think y equals 0, or we can approach it vertically along this line x equals 0. So let's see what happens along those two paths, and then we'll decide where to go from that point. So if we start off with the path x equals 0, this vertical line segment, we look at our limit above, and each and every x becomes a 0. So this would be the limit as 0y approaches 0, 0. And if x is 0, the numerator is 0, and we're divided by 4y squared, which becomes a limit as y approaches 0, but note 0 divided by anything is 0. And if you have any concerns about this limit, as y approaches 0, you assume that y is never equal to 0, just close to it. So this becomes the limit as y approaches 0 of 0, which is 0. Then we look at this horizontal path. When y is 0, we make each and every y turn into a 0. Note the numerator is 0, the denominator is x to the fourth. So similar to our above reasoning, we now have the limit as x approaches 0 of 0, which is still 0. So note along the path x equals 0 and y equals 0, these limits agree. So let me ask you, what do we now need to do? Is there a conclusion that we can draw? And exactly, we cannot make any conclusion. So what we need to do is we need to look at other paths. And at this point, it could be possible that the limit exists and is 0, or if we can find another path where that limiting value is distinct from 0, then we would know the limit does not exist. So a few kind of nice candidates to think about. You could approach the origin along another line segment, maybe along y equals x. That's a reasonable next choice. You could also approach it along maybe more of a quadratic line segment. So something like y equals x squared. And I'm going to give you my intuition. For an example of the form given here, what I would like to do is decide what can I set y or even x equal to combine the denominator into a single term. So note y equals x squared combines the denominator into a single term. And that is a key observation. So because that happens, and will hypothetically make my algebra easier, I'm going to try the path y equals x squared. So similar to what we've done, we are going to take every single y that we see and replace it with an x squared. So x squared times x squared e to the x squared. No, both of those y's became x squareds. Divided by x to the fourth plus 4x squared squared. And let's simplify this a bit. So as x approaches 0, we can simplify the quantity we are taking a limit of. X goes to 0. in the numerator, we have x to the fourth e to the x squared. And in the denominator, note x squared squared really is x to the fourth. So we have x to the fourth plus 4x to the fourth is 5x to the fourth. And it's almost too good to be true here, right? The x to the fourth and the x to the fourth cancel, and we are left with 1/5, a constant that we can pull in front of the limit. And we're taking the limit as x approaches 0 of e to the x squared. And this is a point where we can get a nice reminder from Calculus 1. Note e to the x squared is a continuous function. And just to make the observation kind of below here is that if f is continuous at x equals a, this indicates that the limit as x approaches a of f of x is equal to f of a. That is, a limit of a continuous function is the easiest possible limit to evaluate. You just replace the x's by, in this case, that value a. Because e to the x squared is continuous, we get 1/5 e to the 0, which is 1/5. And note, the limit along the path y equals x squared is 1/5. The limit along the path y equals 0 is 0, which gives us the desired conclusion. Therefore, the limit as xy approaches 0, 0 of x squared y e to the y all over x to the fourth plus 4y squared does not exist. And once again, all of this work that you see kind of in blue is necessary as part of your solution. If you omitted one of the two original paths, x equals 0 or y equals 0, that would be perfectly fine. You just need the two paths that result in distinct limits. So let's conclude this video with another example. And as I oftentimes mention, this is a point where in class I would ask you all to spend a few minutes working an example. So I'm telling you ahead of time, much like I indicated in the previous example, this limit does not exist. And I would like you to determine two paths with different limiting values and fully show your work to explain why this limit does not exist. Okay, so assuming you've paused your video for a few minutes and worked through this, let's go through some details. Now, in terms of starting points, x equals 0, y equals 0, always great choices because those are typically nice, easy values to work with. Now, note in particular our intuition going back to the previous example, if x is 0 or if y is 0, the entire numerator will be 0 while the denominator is not. So those both should give us back the same limit of 0. But even though we can maybe make that observation intuitively, we always go through those details. So if we make each x is 0, so 0y approaches 0, 0, of 0 in the top, y squared in the bottom. This now very conveniently becomes a limit of a single variable, y approaching 0, of 0. So instead of going through the details for the path y equals 0, which we know will result in the same thing, so we'll just say same when y equals 0, let's think about a different path. And the intuition here would be that what could we set y equal to in order to turn that denominator into a single term? So y equals x combines the denominator into a single term. And that's our motivation to go with the path y equals x. And there's no guarantee that things are going to work out nicely or give us what we want. That's just maybe the next logical path that we could try. So we'll go ahead and make each and every y into an x. So it would be x times x cosine of x, all divided by 3x squared plus x squared. And doing a smidge of work, we have the limit as x approaches 0, x squared cosine x over 4x squared. The x squared in the top and the x squared in the bottom cancel. 1/4 is a constant, which pulls in front of the limit. And we're once again left with the limit of a continuous function. And because it's a limit of a continuous function, which we'll hit on in a future video, we can go ahead and substitute that x value in. So no, cosine is continuous everywhere. So specifically, it's continuous at x equals 0. So we have 1/4 cosine of 0. And remember, common value, cosine of 0 is 1. And that does it for us. We now have the limit along two different paths. One of them results in a limit of 0. The other results in a limit of 1/4. So our conclusion is that the limit of interest, so xy approaches 0, 0, of xy cosine y over 3x squared plus y squared does not exist. And at this point, I do want to take a moment to make kind of an observation. You may be thinking that most limits do not exist because that's all we've seen up to this point. But it turns out that we're just investigating limits that do not exist as a starting point because they provide some interesting examples and some good intuition. And in the next video, we will investigate several examples that do exist and the techniques that we need to show that is the case. So stay tuned and take care.